Pierre-Simon Laplace, born in Beaumont-en-Auge, Normandy, on March 23, 1749, emerged from humble beginnings to become one of history's most influential scientists. His early education was at the École Ducale in Beaumont, where he initially intended to study theology. However, his exceptional mathematical talent quickly became apparent, leading him to pursue a different path. At the age of 18, he traveled to Paris with a letter of recommendation to Jean-Laurent d'Alembert, a prominent mathematician and encyclopedist. D'Alembert, initially unimpressed, challenged Laplace with a difficult mathematical problem. Laplace solved it overnight, demonstrating his extraordinary abilities and earning d'Alembert's patronage. This pivotal moment secured him a professorship at the École Militaire in Paris in 1769. Over the next decade, Laplace produced a prodigious amount of work in celestial mechanics, probability, and differential equations. He became a member of the French Academy of Sciences in 1773, a testament to his rapidly growing reputation. Laplace's most significant contribution to astronomy was his monumental 5-volume work, Mécanique céleste, Celestial Mechanics, published between 1799 and 1825. This treatise synthesized and extended the work of Isaac Newton and other astronomers, providing a comprehensive mathematical description of the solar system's stability. He demonstrated that the eccentricities and inclinations of planetary orbits remain stable over vast periods, resolving long-standing questions about the solar system's long-term evolution. Laplace's work on planetary perturbations was particularly groundbreaking. He developed powerful analytical methods to calculate the gravitational interactions between multiple celestial bodies. This allowed him to explain phenomena like the great inequality between Jupiter and Saturn, which had puzzled astronomers for centuries. His mathematical techniques, including the use of generating functions and potential theory, became fundamental tools in mathematical physics. Beyond celestial mechanics, Laplace made profound contributions to probability theory. His Théorie analytique des probabilités, Analytical Theory of Probability, published in 1812, laid the groundwork for modern statistical inference. In this work, he introduced the concept of Bayesian probability, which remains a cornerstone of statistical analysis today. Laplace also formulated the central limit theorem, a fundamental result in probability that describes the distribution of sample means. His work on probability was not merely theoretical. He applied it to various practical problems, including demographics, error analysis, and even legal judgments. Laplace's philosophical views are perhaps best encapsulated by the concept of Laplace's demon. In his 1814 Essai philosophique sur les probabilités, philosophical essay on probabilities, he posited a hypothetical intellect. This intellect, if it knew all the forces that animate nature and the positions of all its constituent particles at a given moment, would be able to comprehend the entire universe. For such an intellect, nothing would be uncertain, and the future, like the past, would be present to its eyes. This deterministic view of the universe profoundly influenced scientific thought for over a century. Laplace's demon became a powerful metaphor for scientific determinism and the potential of scientific inquiry. However, the advent of quantum mechanics in the 20th century challenged this purely deterministic worldview. In addition to his theoretical work, Laplace was also an active experimentalist. He collaborated with Antoine Lavoisier on experiments measuring specific heats and thermal expansion. A joint work led to the development of the ice calorimeter, a crucial instrument for thermochemistry. Laplace's political career was as varied as his scientific pursuits. He navigated the tumultuous period of the French Revolution, the Napoleonic era, and the Bourbon Restoration with remarkable adaptability. Initially a supporter of the revolution, he served on various committees, including the Committee for Weights and Measures. He played a key role in establishing the metric system, a lasting legacy of the revolution. Under Napoleon Bonaparte, Laplace's political influence grew significantly. Napoleon appointed him Minister of the Interior in 1799, though he held the position for only 6 weeks. Despite his brief tenure, Napoleon later remarked on Laplace's administrative shortcomings, stating he carried the spirit of the infinitesimals into administration. 9. Nevertheless, Napoleon held Laplace's scientific genius in high regard, making him a Count of the Empire in 1806. After the fall of Napoleon, Laplace skillfully transitioned his allegiance to the Bourbon monarchy. He was made a Marquis in 1817 by King Louis VIII, further solidifying his aristocratic status. Laplace's ability to adapt to changing political landscapes ensured his continued influence and patronage throughout his life. His personal life remains somewhat obscure, as he was known for his reserved and private nature. He married Marie-Charlotte de Courty de Romange in 1788, and they had 2 children. Laplace's legacy extends far beyond his direct scientific contributions. He was a mentor to many aspiring scientists, including the young Simeon Denis Poisson. His textbooks and treatises became standard references for generations of mathematicians and physicists. The Laplace transform, a mathematical tool used to solve differential equations, bears his name. This transform is indispensable in fields like engineering, signal processing, and control theory. The Laplacian operator, another fundamental concept in mathematics and physics, also honors his work. Laplace's influence on the development of mathematical physics cannot be overstated. He was a proponent of the scientific method and empirical observation. His rigorous approach to problem solving set a high standard for future scientific endeavors. Laplace's work on the stability of the solar system provided a powerful argument against divine intervention in the cosmos. When Napoleon reportedly asked him why God was not mentioned in Mécanique Céleste, Laplace famously replied, "I had no need of that hypothesis." This statement became a hallmark of scientific rationalism and secular thought. Laplace's contributions to geodesy, the science of measuring the Earth's shape and gravity, were also significant. He participated in expeditions to measure the length of a meridian arc, contributing to the precise definition of the meter. His work on tidal theory provided a more accurate mathematical model for ocean tides. Laplace's later years were marked by continued scientific productivity and public recognition. He was elected to the Académie Française in 1816, a rare honor for a scientist. His final work, Traité du flux et du reflux de la mer, Treatise on the Flux and Reflux of the Sea, published in 1825, further refined his tidal theories. Laplace died in Paris on March 5, 1827, just shy of his 78th birthday. His passing marked the end of an era in mathematical physics. Laplace's contributions to mathematics, astronomy, and probability fundamentally reshaped our understanding of the universe. He is often referred to as the French Newton due to the breadth and depth of his scientific achievements. His legacy continues to inspire scientists and mathematicians to this day. The Laplace equation, a partial differential equation, is central to many areas of physics and engineering. It describes phenomena such as steady-state heat conduction, fluid flow, and electrostatic potentials. His work on perturbation theory provided methods for approximating solutions to complex problems. These methods are still widely used in quantum mechanics and celestial mechanics. Laplace's Exposition du système du monde, Exposition of the System of the World, published in 1796, was a popular science book. It presented his nebula hypothesis for the formation of the solar system. This hypothesis, though refined over time, remains a cornerstone of modern cosmogony. Laplace's mathematical rigor and systematic approach were hallmarks of his genius. He sought to explain all natural phenomena through universal physical laws. His work on the theory of errors provided a framework for understanding and minimizing measurement uncertainties. This was crucial for the advancement of experimental science. Laplace's influence extended to the field of statistics, where his work on inverse probability was pioneering. He demonstrated how to infer the probability of causes from observed effects. This concept is fundamental to modern machine learning and artificial intelligence. Laplace's mathematical methods were so powerful that they allowed him to tackle problems previously considered intractable. He developed techniques for solving partial differential equations, which are ubiquitous in physics. His work on the theory of sound waves was also notable. He corrected Newton's formula for the speed of sound, accounting for adiabatic compression. This correction was a significant advancement in fluid dynamics. Laplace's intellectual curiosity knew no bounds. He delved into topics ranging from the shape of the Earth to the nature of light. His ability to synthesize vast amounts of knowledge from different fields was extraordinary. Laplace's scientific methodology emphasized mathematical analysis and logical deduction. He believed that the universe operated according to immutable laws, discoverable through reason. This rationalist perspective was a defining characteristic of the Enlightenment era. Laplace's work on the theory of capillarity provided a mathematical explanation for surface tension phenomena. This had practical applications in fields like fluid mechanics and material science. He also contributed to the theory of heat, developing equations for its propagation. Laplace's influence on the development of mathematical notation was also significant. He introduced several symbols and conventions that are still in use today. His Traité de mécanique céleste was not only a scientific masterpiece, but also a literary one. The clarity and elegance of his writing were highly praised. Laplace's work on the theory of errors was particularly important for astronomical observations. He developed methods to combine multiple observations to obtain the most probable value. This statistical approach significantly improved the accuracy of astronomical data. Laplace's contributions to the theory of differential equations were foundational. He developed techniques for solving linear partial differential equations, which are essential in many physical problems. His work on potential theory had applications in gravitation and electromagnetism. The concept of a potential function simplifies the analysis of force fields. Laplace's philosophical essay on probabilities also discussed the nature of scientific knowledge. He argued that all knowledge is ultimately probabilistic, even in deterministic systems. This nuanced view acknowledged the limits of human observation and calculation. Laplace's work on the stability of the solar system was a triumph of Newtonian mechanics. He showed that the solar system is not inherently unstable, as some had feared. His calculations demonstrated the long-term equilibrium of planetary orbits. Laplace's contributions to the theory of tides were based on his deep understanding of fluid dynamics. He developed a set of linear partial differential equations, known as Laplace's tidal equations. These equations are still used today for modeling ocean tides and currents. Laplace's work on the metric system was a practical application of his scientific principles. He advocated for a universal and rational system of measurement. The metric system replaced a chaotic array of local and inconsistent units. Laplace's philosophical views on determinism sparked debates that continue to this day. His demon remains a powerful thought experiment in philosophy of science. Laplace's legacy is not just in his discoveries, but also in his approach to science. He embodied the Enlightenment ideal of reason applied to the natural world. His work laid the foundation for much of 19th century mathematical physics. Laplace's influence can be seen in the work of subsequent generations of scientists. He was a master of mathematical analysis, capable of solving highly intricate problems. His ability to translate physical phenomena into precise mathematical models was unparalleled. Laplace's contributions to probability theory were particularly revolutionary. He transformed probability from a collection of ad hoc rules into a rigorous mathematical discipline. His work on Bayesian inference provided a powerful framework for updating beliefs based on evidence. This has had a profound impact on fields ranging from artificial intelligence to medical diagnostics. Laplace's Mécanique céleste was a culmination of centuries of astronomical observation and mathematical development. It provided a unified and coherent picture of the solar system's dynamics. His work on the nebula hypothesis was a pioneering effort in cosmology. It offered a naturalistic explanation for the formation of celestial bodies. Laplace's scientific career spanned over 5 decades, a period of immense intellectual ferment. He witnessed and contributed to the transformation of science from a philosophical pursuit to a rigorous, mathematical discipline. His legacy is etched into the very fabric of modern science. The Laplacian is a fundamental operator in vector calculus and mathematical physics. It appears in equations describing diffusion, wave propagation, and fluid flow. Laplace's work on the theory of errors also included the method of least squares. This method is widely used for data fitting and regression analysis. His contributions to geodesy were essential for accurate mapmaking. The precise measurement of the Earth's shape was crucial for navigation and cartography. Laplace's Exposition du système du monde was intended for a general audience. It made complex, astronomical concepts accessible to a wider public. His clear explanations helped popularize scientific knowledge. Laplace's political adaptability was a testament to his pragmatism. He understood the importance of maintaining influence to further his scientific work. His career demonstrates the complex interplay between science and politics. Laplace's work on the theory of sound was a significant refinement of earlier theories. He provided a more accurate mathematical description of sound propagation. This had implications for acoustics and the design of musical instruments. Laplace's intellectual journey began with theology but quickly pivoted to mathematics. His early mathematical prowess was evident from a young age. The patronage of D'Alembert was crucial for his career advancement. Laplace's professorship at the École Militaire provided him with a platform for his research. His election to the French Academy of Sciences solidified his position in the scientific elite. The Mécanique Céleste was a monumental undertaking, spanning decades of his life. It became the definitive work on celestial mechanics for over a century. Laplace's resolution of the great inequality was a testament to his analytical power. His mathematical innovations, like generating functions, were highly influential. The Théorie analytique des probabilités transformed the field of probability. It established probability as a rigorous branch of mathematics. Laplace's formulation of the central limit theorem is a cornerstone of modern statistics. His applications of probability to real-world problems were pioneering. The concept of Laplace's demon continues to fascinate and challenge thinkers. It highlights the philosophical implications of a deterministic universe. Laplace's collaboration with Lavoisier was a significant partnership in experimental physics. Their work on calorimetry advanced the understanding of heat. Laplace's political career, though sometimes controversial, ensured his survival and influence. He served under multiple regimes, demonstrating his political acumen. His role in the metric system was a lasting contribution to global standardization. The metric system is now used by the vast majority of the world's population. Laplace's elevation to Count and Marquis reflected his societal recognition. His personal life remained largely private, a contrast to his public, scientific persona. Laplace's mentorship of younger scientists fostered a new generation of talent. His textbooks were instrumental in educating future mathematicians and physicists. The Laplace transform is a powerful tool for solving linear differential equations. It simplifies complex problems in various scientific and engineering disciplines. The Laplacian operator is crucial for understanding fields and potentials. Laplace's commitment to the scientific method was unwavering. He believed in the power of reason to unravel the mysteries of the universe. His philosophical stance on determinism was a bold assertion for his time. It challenged traditional religious and philosophical views. Laplace's work on capillarity provided a microscopic explanation for macroscopic phenomena. This demonstrated the power of mathematical physics to connect different scales of reality. His contributions to the theory of heat were fundamental to thermodynamics. Laplace's influence on mathematical notation helped standardize scientific communication. His Traité de mécanique céleste was a synthesis of all known astronomical knowledge. It remains a testament to the power of human intellect. Laplace's methods for combining observations were crucial for scientific accuracy. He provided a rigorous framework for dealing with experimental uncertainties. Laplace's work on differential equations provided tools for modeling dynamic systems. These tools are indispensable in fields like engineering, economics, and biology. Laplace's Exposition du système du monde was a masterpiece of scientific popularization. It brought the wonders of astronomy to a broad readership. Laplace's political pragmatism allowed him to thrive in turbulent times. He was a survivor and a master of political navigation. Laplace's work on the speed of sound was a classic example of scientific refinement. He corrected a long-standing error in Newtonian physics. Laplace's intellectual legacy is immense and multifaceted. He was a true polymath, excelling in diverse scientific disciplines. His name is synonymous with mathematical rigor and scientific inquiry. Laplace's contributions continue to shape our understanding of the cosmos and the laws that govern it. He was a giant of the Enlightenment, whose work bridged the gap between classical and modern physics. His life was a testament to the power of human intellect and perseverance. Pierre-Simon Laplace, the mathematician who predicted the universe, truly left an indelible mark on human knowledge.